So let's begin. This first problem we're going to do is going to be an example of a total value problem. So, example 1. So, in order to pick up lunch, Kathy collects $181.50. She collects $181.50 from her co-workers for a total of 21 salads and sandwiches. Okay, so she collected this $181 for a total of 21 sandwiches and salads. When she got to the deli, she forgot how many of each the people ordered. If salads cost $7.50, that's for a salad. And if sandwiches cost $9.50, how many of each should she buy? So that's the setup. Kathy is probably ordering lunch for a bunch of her co-workers. She took 21 different orders, and she collected a bunch of money, and the total amount that she collected was $181.50. She forgot how many of each she was going to buy, but she does know the prices of each of the items being sold. So, we've got two bits of information here. I'm going to let X equal the number of salads, ADS, and we'll let Y be equal to the number of sandwiches. So we know two bits of information. First off, we know that the number of salads plus the number of sandwiches has to equal 21. We also know that $7.50 times the number of, let's see, X was salads, times the number of salads, plus $9.50 times the number of sandwiches has to equal $181.50. At this point, we've set up a system of equations to model this problem. We know that x plus y has to equal 20, and we can rewrite this. X plus y equals 21, and we know that 7.5x plus 9.5y has to equal 181.5. So at this point, we've set up the problem. You're free to solve these problems with whatever method you want. You could solve them by graphing, you could solve them by substitution, you could solve them by elimination. In my experience, real-world problems are typically easiest when you go by substitution. This top equation would be really easy to solve for one of the variables, and we could plug it into the bottom equation, and that's going to be our approach for this problem. So let's go forward and actually try and solve this problem. Let's figure out how many of each Kathy needs to buy. I'm running out of space, so I'm just going to rewrite. Well, we've got some room down here. We know that x plus y is equal to 21. I'm going to solve for x. Why not? That means x is equal to 21 minus y. We're going to take this equation and we're going to plug it into the equation we haven't used, and we're going to figure out how many salads Kathy needs. So let's do that. We know that, I'm just going to rewrite, x is equal to 21 minus y, and 7.5x plus 9.5y is equal to 181.5, I believe. 181.5. Well, that means that 7.5 times 21 minus y plus 9.5y is equal to 181.5. Now that we have substituted this top equation into the bottom equation, we're just trying to solve for y. So what we want to do is we want to take this 7.5 and we're going to distribute it to the 21 and a cross subtraction to the y. 7.5 times 21, 21, we multiply, 5, 7, 0, 0, 15, 5, 7, 5, 1, and I need a decimal. So we get 157.5 minus 7.5y plus 9.5y is equal to 181.5. Just distributing. Now let's gather some like terms. I'm just going to work with this left-hand side of the equation real quick. The 157.5 will move over in a second. If we have negative 7.5y and we add 9.5y, well, that's going to leave us with a positive 2y left over, and that still is going to equal 181.5. Now let's get 2y all by itself. We can subtract 157.5 from both sides, minus 157.5. And 181.5, then 157.5. We go through and subtract those. 0, 4, 2. So we get 2y is equal to 24. Divide both sides by 2. And we get y is equal to 12. Now that we know what y is equal to, let's go back up to this top equation. We know that x is going to be equal to 21 minus y, and y is 12. That means x is going to be equal to 21 minus 12. And that means x has to be equal to 9. X is equal to 9. But we have to answer the question in the context of the question. And by that I mean just saying x is equal to 9 and y is equal to 12. They're perfectly good answers to this problem. But what we were doing is we were trying to solve Kathy's problem. Kathy forgot how many salads and sandwiches she ordered, so we need to answer the problem in the context of the problem. So if x was 9 and x was the number of salads, that means Kathy needs to buy 9 salads and 12 sandwiches. But this is going to be our overall process for solving total value problems. For a total value problem, we're going to get some information about the total quantity, and we're going to get some information about the total price. We're also going to get some information about how much each of the items cost by themselves. We can make one statement about the total items sold, and we make one statement about the total cost of the purchase. Once we set up this system of equations, then you're free to solve this by whatever method you want. We could have gone through and multiplied both sides of this equation by, say, a negative 7.5 and tried to use elimination. For problems like this, substitution is a pretty quick and easy method, especially when we don't have to do any division to isolate one of the variables. So we chose substitution. We rearranged one of the equations, plugged it into the other, got one of our variables, and then we solved for the other one. And then remember, story problems, your answer isn't values of variables. Your answer is typically words. Your answer is an answer to a real world problem. In this case, Kathy forgot how many lunches to buy. So let's do another example. This one's going to be a little bit different. This is also what I would consider a total value problem. It definitely has elements of mixture problems. Let's just go over it. So Summit Spice and Tea Company sells ground turmeric for $1.35 per ounce and ground sumac for $1.85 per ounce. Ethan wants to buy a 20-ounce seasoning bag, Ethan wants to make a 20-ounce seasoning blend of the two spices that sells for $1.65 per ounce. How many of each should he use? Okay, so Summit Spice, they sell turmeric and sumac. Their turmeric is going to sell for $1.35 per ounce, and their sumac is going to sell for $1.85 per ounce. And what Ethan wants to do is they're going to combine turmeric and sumac into one spice blend, and they want that spice blend to have a value of $1.65 per ounce. So we need some variables here. Let's let x be equal to the number of ounces of turmeric. And let's let y be equal to the number of ounces of sumac. And so what do we know? We know that Ethan wants to take turmeric and sumac, and he wants to make a 20-ounce blend. So that means the number of ounces of turmeric plus the number of ounces of sumac need to equal 20. Now, the next equation is going to be a little bit different than what we did on the example before. We still want $1.35 times the number of ounces of turmeric plus $1.85 times the ounces of sumac. But now the total cost is going to be equal to $1.65 times the total number of ounces that we get. You can think of it as x plus y. The amount we pay for turmeric plus the amount we pay for sumac is going to equal the blend times the total mixture, how many ounces we're putting in there. So this can be our system of equations. I'm going to rewrite this top equation a little bit differently. So working with this 135x plus 185y being equal to 1.65 times x plus y. Before I go on, what I'm going to do is I'm going to distribute and I'm going to simplify a little bit. What we could also do, and I'm not going to go about it this way, but you could, we know that what x plus y is. X plus y is 20. So we could directly plug in 20 for here and then just get a number on the right hand side. Definitely a good approach to this problem. I'm going about it a different way. More than one way to solve a problem. So working with this bottom equation, we still get 135x plus 185y, but that's going to be equal to 165 times x plus 1.65y. I'm going to subtract. I'm going to gather some like terms. Move all my x's to the right hand side and all my y's to the other. Minus 135x minus 135x minus 165y minus 165y. These will cancel. And we'll go through and subtract these. That will actually give us 0.2y. And 0.2y had better be equal to 0.3. 3x. We can multiply both sides of this equation by 10 just to clear out those decimals to get 2y is equal to 3x. So all we did here was simplify our system of equations. This equation is equivalent to this bottom equation. That means this system of equations is equivalent to this system of equations. And this second system of equations might be a little bit more convenient for us to work with. So once again, I'm going to solve using the process of substitution. I'll take this top equation and I'll solve for y. We'll get y being equal to 20 minus x. And now that we know what y is, let's plug it into the bottom equation. I'm just going to rewrite this system and that equation on the backhand side. We knew that x plus y had to equal 20, and we knew that 2y plus 3x, 2y was equal to 3x. And from that top equation, we rewrote as y being equal to 20 minus x. So that means this bottom equation, 2 times y is equal to 3x. That means 2 times 20 minus x is equal to 3x. Substitution. Oh, now we're going to distribute 2 across subtraction to get 40 minus 2x being equal to 3x. Gather some like terms. We get 40 being equal to 5x. And that gives us x is equal to 8. Once we know what x is equal to, we can plug it into either of these equations. I'm going to use that top equation. If x plus y is equal to 20 and x is equal to 8, that means 8 plus y is equal to 20. Subtract 8 from both sides. Gives us y is equal to 12. But remember, this problem didn't ask us about the values of x and y. We came up with the variables x and y to help us solve the original problem. What this problem was asking us about was how many ounces of turmeric and how many ounces of sumac Ethan needed. So we got that Ethan needs 8 ounces of turmeric and 12 ounces of sumac to do what? To make the desired spice blend. So let me reread this question to you and let's go over it. Summit Spice and Tea Company, they sell ground turmeric for $1.35 per ounce, and they sell ground sumac for $1.85 per ounce. This gentleman Ethan came along, and Ethan wanted to make a combination of turmeric and sumac. And he wanted the combined value of that spice blend to be equal to $1.65 per ounce. He also wanted to make 20 ounces in total. So we came up with one equation that modeled the total quantity, the total volume, how much, and then we came up with another equation that modeled how much it was going to cost. Like I said, this bottom equation, arrows going everywhere, we could have written as 1.35x plus 1.85y was equal to 1.65 times 20, the total value, and this would make it similar to the problem we did before. But I worked this problem off camera, and I liked getting it to this point. No, you could have rewritten this bottom equation like we had over here, and then solving example 2 and example 1 would have been identical. But we chose a different route. And then we, once we had our two systems of equations, we manipulated them until they were a little bit easier to work with. And then we went through with the system of, or with the method of substitution. We picked one equation, we solved for one of the variables, substituted it into the other equation, and then came up with a number. We took that number, we plugged it into either of these equations. Both of them would have given us the same answer. Yeah, both of them would have. And we solved for the missing variable. The final step in these story problems is that, remember, we're solving a story. Ethan is trying to make a spice blend, so we need to help Ethan out. We need to let him know how many of each spice he needs to get. So our answer for story problems is definitely going to be this statement about what our variables mean. But for total value problems, that's it. You want to come up with an equation that models how much, an equation, or let's say it differently. We want to come up with an equation that models how many, and one equation that models how much. So now that we've done two examples of total value problems, let's do an example of a mixture problem. So, nature's landscapes carries two kinds of fertilizer containing nitrogen and water. Gently Green is 5% nitrogen, and Sun Lover is 15% nitrogen. Nature's landscape needs to combine the two types of solution in order to make 90 liters of solution that is 12% nitrogen. How many of each should be used? So, for mixing problems, we're going to have a statement about the total volume of solutions being used, and we're going to have some statement about their concentrations. So let's go through this again. Nature's landscape, they carry two kinds of fertilizer containing nitrogen and water. Gently Green, which I'm going to call GG. Gently Green is 5% nitrogen. I believe nitrogen is just a capital N. And then Sun Lover, which I'm going to call SL, well, that's going to be 15% nitrogen. And what this company wants to do is they want to combine some amount of Gently Green and some amount of Sun Lover to get a final volume of 90 liters at 12% concentration. So, we want to come up with a statement about total volume and a statement about concentration. We need to declare some variables first. So let's let X be equal to the number of liters of Gently Green, and let's let Y be equal to the number of liters of Sun Lover. And so what do we know? We know that this company, they want X plus Y, or after they get done combining some amount of Gently Green and some amount of Sun Lover, they want to have 90 liters of a solution lying around. And now we need a statement about the concentration. Well, we know that the volume of Gently Green times its concentration, and concentrations are going to be written down as a decimal. So the volume times the concentration, volume times concentration plus volume times concentration, 15% is 0.15, has to equal volume times concentration. So you've got volume plus volume is equal to volume, and you have volume times concentration plus volume times concentration is equal to volume times concentration. Once we're at this point, we have successfully identified our system of equations. I'm going to go through and I'm going to simplify this bottom equation just to put it in a form that's a little bit easier for us to work with. We still know that x plus y has to equal 90. And I'm gonna just rewrite this bottom equation. I'm gonna gather some like terms on the right hand side, and the left is gonna stay the same. So 0.05x plus 0.15y, that has to be equal to 90 times 0.12. Well, 90 times 12 is 108, and that would tell us to bump the decimal twice to the left, and that would have us bump it once to the right. 90 times 0.12 is 10.8. So this is our new system of equations. Once again, this is a perfect form for us to work with if we're going to use some sort of computer, some sort of calculator to help us solve this problem. I'm going to be doing this problem by hand, so I'm going to go through and I'm going to clear out these decimals. So I'm going to multiply both sides of this equation by 10 just to make it easier to work with. And we'll get the new system of equations, or the equivalent system of equations. X plus y is equal to 90, and we bump that decimal up to, I want to multiply by 100, not 10, I'm sorry. We'll bump that decimal 1, 2 to get 5x plus 15y is equal to 1080. And this is going to be the system I'm going to work with. Like I said, this system would have been perfectly fine. I'm going to do this by hand, and I wanted to clear out those decimals to make life a little bit easier for me. And up until this point, we have solved both of the previous examples with substitution. And I've said that you can solve them with any method you want to. Though it's set up to be, I don't want to say it's set up to be solved by substitution. It seems easy to solve this problem by substitution. Easy in that we don't have to work terribly hard to set it up to do it. Let's solve this one by elimination, just for the sake of doing it that way. Remember, to solve by the method of elimination, you need leading coefficients that are opposite in sign. We don't have that here. So we're going to want to manipulate one of these equations and make it look like the other. Well, let's go through actually. Let's take this bottom equation and let's divide both sides by -5. So we'll divide this side by a -5 and this side by a -5. That will give us, I'm going to rewrite this top equation, x plus y being equal to 90. It's just along for the ride right now. And 5 divided by -5 will give us a -x. 15y divided by -5 will give us -3y. And then 1080 and a 5. 0, 1, 5 will give us a -216. So, this is our new system of equations. Did I do that right? 216 times 5. Yeah, did that right. Perfect. So this is our new system of equations. I went through and I divided both sides by -5. So we had a positive x and a negative x. Now going through with the method of elimination, we're going to take these two equations and add them together. X plus y is equal to 90, and -x minus 3y is equal to -216. And we'll go through and add them. Make sure you have an x column, a y column, and a constant column. X plus -x gives us no x. Y, take away 3y, gives us a -2y. And 90 take away 216. If we had 216 and we took 90 from it, 6, 1, 2, and then we need a 1 down there, is equal to -126. Divide both sides by -2 to get y is equal to 63. Once we know one of the variables, go back to either of your equations and plug it in. This top equation is a little bit easier to work with. So let's work with that top equation. And to not get too much on one page, I'm gonna take that top equation and that value to the next page. We know that x plus y had to equal 90, and we know that y is equal to 63. That means x plus 63 has to be equal to 90. Subtract 63 from both sides. That means x is going to have to be equal to 27. Yep, x is equal to 27. But remember, this problem didn't ask us about the values of x and y. They asked us for how many liters of each fertilizer we needed to use. So we know we need to use 27 liters of gently green, I believe was x, of gently green needs to be mixed with, 63 liters of sun lover to make 90 liters, we'll say at a concentration of 12%. For our final solution. I have a typo in my answer. That's right, though. So, what do we do here? Let's go over the problem. Nature's Landscapes carries two kinds of fertilizer, Gently Green and Sun Lover. Gently Green is 5% nitrogen, Sun Lover is 15. We want to combine these two, make 90 liters at a 12% concentration. For mixing problems, have one equation about your volume, how much, and then have your second equation be about the concentration. So we've got an equation about volume, an equation about concentration. For your equation regarding concentration, what we have is we have a volume times a concentration plus a volume times a concentration is equal to a volume times a concentration. And these last ones are your final volume times your final concentration. So x plus y was equal to 90, and x times its concentration of 5%. And remember, percentages get recorded as decimals. X times 0.5 plus y times 0.15 was equal to the final volume times the final concentration. From that point, that was setting up the system of equations. This was simplifying the right-hand side, and getting down here, it was just putting it in a form that was easy for me to work with. Could have solved this system by any method, substitution, elimination, or by graphing. I wanted to give you an example of elimination, so that's why we chose that method. If I wasn't trying to refresh your memory, if I wasn't teaching you, I probably would have gone with substitution like I have the rest of them. These problems are pretty straightforward with substitution, but I wanted to show you elimination again. So that's what we did. We made it so our leading coefficients were opposite in sign. I chose to divide both sides of this bottom equation by -5 in order to get that. We had an x and a negative x, so when we combined them, that eliminated our x's. And then we combine our y's and our constants. Once we solve for one variable, we were free to plug it into either equation. Typically, one is going to be easier to work with than the other, and we solved for the other variable. Thing to remember is this problem never asked us about variables. This problem asked us about this real-world problem. So our answer looks like a solution to a real-world problem and not necessarily just an answer to a purely mathematical problem. The next example that we're going to go through, example 4, is a lot like a mixture problem, but it isn't necessarily dealing with concentrations. It's going to be dealing with insurance rates, or not insurance rates. I'm sorry, interest rates. So, Jerome has some student loans. Jerome's student loans total to is $16,200. So Jerome has $16,000 worth of student loan debt. Part of his student loan was a Perkins loan, and that Perkins loan was at a 5% interest rate, and the rest was a Stafford loan. And that was at 4% interest rate. After 1 year, Jerome's loans had accumulated, so after 1 year, Jerome had accumulated $715 worth of interest. What was the amount of each loan? So Jerome, $16,200 worth of student loans, has a Perkins loans and a Stafford loan. The problem didn't state it explicitly, but I am going to assume that interest is compounded once per year. And we're tasked to figure out how large his Perkins loans was and how large his Stafford loan was. So once again, we want to come up with a statement about total quantity, and now we're going to make a statement about interest rates. So let's start off. We need to declare some variables. Let's let x be equal to the value of Perkins loan, and we'll let y be equal to the value of the Stafford loan. So what do we know? We know that the value of the Perkins loan plus the value of the Stafford loan is going to be equal to the value of the loan in total, $16,200. And we also know that the interest we pay on the Perkins loan, 0.05 times x, plus the interest we paid on the Stafford loan, 0.04 times y, is going to be equal to $715. And so this is our system of equations. We know that the value of this loan plus the value of the other loan is equal to the value of the loan in total, and we know that the interest paid on this part of loan plus the interest paid on this part of the loan is equal to the total interest. Once again, I'm going to go through and I'm just going to rewrite this bottom equation, make it look a little bit nicer to me. And then, yeah, we will continue. Yeah, we'll just do that. So let's say x plus y is equal to 16,200, and let's say that, yeah, I'm debating on whether or not I want to move my decimal. It's nice to clear out decimals, but we're also going to sum in a fairly large number on the right-hand side. Let's go ahead and do that. I'm going to go through and multiply both sides of this equation by 100. Keep on doing that. To get 5x plus 4y has to equal 715 with 2 more zeros. So this is our new system of equations. It's equivalent to the one above. It's just in a form that might be a little bit easier for me to work with. Oh gosh, I'm trying to figure out if I want to go through and if I want to solve with substitution or elimination. I tend to not like to substitute in larger values if I can help it. Most of my experience in math class, I have not been able to use a calculator, so I've learned how to kind of avoid large numbers. larger numbers. So let's go through and let's do elimination like in the previous problem. And the last problem, we wanted to eliminate x's, so in this problem, let's eliminate y's. We're going to leave this bottom equation alone. 5x plus 4y has to equal 71,500. But that top equation, let's multiply both sides by a -4. That'll give us -4x minus 4y. Oh, and we need to multiply 16,200 by 4. 0, 0, 8, 6, 12, 24, 4, 5, 6, 64,800, but we multiplied it by -4, so that would be equal to a -64,800. We did that so we could have these two leading coefficients that were opposite in sign. We're going to go through and we want to add these two equations together. -4x plus 5x gives us just x all by itself. -4y plus 4y, those are going to cancel each other out. Now we get the joy of trying to subtract 64,800 from 71,500. Go through and subtract these. 0 and 0, that's the easier part. 0, 15, 7, 10, and 6. 6,700. X is equal to 6,700. Now that we know what x is, we could pick either of these equations. One of them is going to be a whole lot easier to work with, so let's do that. We know that the sum of x and y is 16,200. And we learned that x was 6,700. That means that 6,700 plus y has to equal 16,200. Oh, we can subtract 6,700 from both sides. And we go through and subtract those. 0, 0. Oh, that's going to be a 5. That 2 is going to be a 5. And then that's going to be a 9. So we get y to be equal to 9,500. Yeah. Y is equal 9,500. Sorry, I got excited. I checked the answer to make sure I got it. And x was 6,700, 6,700, however you want to say it. Like I've said over and over again, this problem wasn't asking us about the values of x and y. They were asking us about the amount of a loan. So we need to answer, our answer needs to make sense in the context of this question. X was equal to the value of Perkins loans. And how do you spell Jeroen's name? Jeron. Jeroen took out a $6,000. I've never understood why the unit comes first with dollars. Jeroen took out a $6,700 Perkins, was it? Perkins loans. And a $9,500 Stafford loan. So we answered the problem, or we gave an answer that made sense in the context of this problem. Now let's talk about motion problems. For motion problems, we're gonna use a formula. D is equal to RT, or the distance. The distance something travels is equal to the rate it travels times the time, or how long they've been going. So you can think of this as how fast times how long is equal to how far. So an example. Carrie left Monday morning to drive to a seminar that began Monday evening. An hour after she left the office, her assistant realized that she had forgotten a large portfolio. The assistant left immediately with the portfolio to try and catch up with Carrie. If Carrie drove at 55 miles per hour and her assistant drove at 65 miles per hour, how long did it take for the assistant to catch up with her? So, this problem doesn't have, and let's give the assistant a name. The assistant's name is Matt. So we'll have a Carrie equation and we'll have a Matt equation. And both of them are going to be of the form distance is equal to rate times time. We don't know the distance. It didn't say the distance. So we're just going to put a D. The distance that Carrie is driving is equal to the rate. And now we know the rate. We know that Carrie is driving at 55 is equal to 55 times the amount of time that she's been driving. And we're going to let T be equal to number of hours. Now her assistant, Matt, he goes some distance, but his rate is going to be different. Matt is driving 65 miles an hour, but in the problem it said Matt didn't notice the portfolio was still at the office until an hour after Carrie left. So the number of time, or the length of time that Matt has been driving is going to be T minus 1. So we now have these two equations. We know that the distance Carrie drives is equal to 55 times T, and we know that the distance Matt drives is going to be equal to 65 times T minus 1. So now we want to go through and we want to solve this system of equations. We've got this system right here. But check it out. If we know that 55T is equal to D, that's what it says in this top equation, I just wrote it backwards. 55T is equal to D. Well, in this bottom equation, we know D is equal to 65 times T minus 1. So if 55T is equal to D, and if D is equal to 65 times T minus 1, that means 55T had better be equal to 65 times T minus 1. Okay? We're just kind of not dropping, we're ignoring, we're looking at the two outsides of that equation. Now we've got one equation and one unknown. We can solve that. Let's distribute. We can distribute that 65 over subtraction. Get 55T being equal to 65T minus 65. We want to get T all by itself, so let's subtract 55T from both sides. And let's add 65 to both sides to get 65 is equal to 10T. Divide both sides by 10, divide both sides by 10, and we get T is equal to 6.5. That's wonderful. We've came up with a beautiful number, but we need to say what this means in the context of the problem. So our final answer would be a statement kind of like, oh, it took Matt 6.5 hours. Well, you got to be careful what T actually means. So the amount of time that Matt was driving was actually T minus 1. So it took Matt 5.5 hours to catch Carrie. Or you can think that Carrie drove for 6.5 hours before Matt caught her. Caught up. So this is why the statement is very important. And why you need to be careful about what it is you're actually answering. If the question is asking how long it took Matt to catch Carrie, well, it only took Matt 5.5 hours to catch Carrie. But if the question was how long was Carrie driving, well, Carrie drove for a total of 6.5 hours before Matt caught up with her. Let's read this question again. Carrie left Monday morning to drive to a seminar that began Monday evening. An hour after she had left the office, her assistant Matt realized that she had forgotten to take a large portfolio needed for a presentation. Knowing Carrie would not answer her cell phone when driving, Matt left immediately with the portfolio to try and catch up with her. If Carrie drove at a speed of 55 miles per hour and Matt drove at a speed of 65 miles per hour, how long did it take for Matt to catch up with her? Okay, so we're asking about the amount of time Matt was in the vehicle, and though t was equal to 65, this Matt equation says that Matt was only going to drive for 6.5 minus 1, or 5.5 hours to catch up with Carrie. So be very careful. Even though through this problem we got t was equal to 6.5, what we were actually after was 5.5. So you've got to ask yourself, does this answer make sense in the context of the problem? That's a good spot to kind of bring up this point. We're dealing with real world quantities here. So you shouldn't, general rule of thumb is you should never cut people in half. It's a bad idea to cut people in half. They don't like it. Halves, thirds, quarters, it doesn't matter. We don't like to be cut. And in saying those mixing problems, you can't have a negative amount of volume. So you need to ask yourself if your answer, well, first off, does your answer make sense in the context of the problem? Is distance positive? Is time moving forward? Have I accidentally cut someone in half? So you have to ask yourself, does your answer make sense in the context of the problem? And then you have to answer the problem in terms of what is being asked. It's something you guys should get used to over and over and over again, asking yourself, does this answer make sense? So when you're going through and doing these story problems, ask yourself, does the answer make sense in the context of the problem? So let's go over one final example. A Coast Guard patrol boat travels 4 hours on a trip downstream with a 6 mile per hour current. The return trip against the same current takes 5 hours. Find the speed of the boat in still water. So we've got this Coast Guard boat. I'm going to draw a picture for this one. We've got a current, it's going that way. We've got a little boat. And we've got someone from the Coast Guard in it. So when they're traveling with the current, they travel with the current for 4 hours. And when they're fighting the current, so current going that way, and now the boat is going that way, it takes them 5 hours. And we want to know the speed of the boat in still water. So this is another motion problem. For motion problems, we're going to use the equation d is equal to rt. Distance is equal to rate times time. How far is equal to how fast times how long. For motion problems, distance is equal to rate times time. Students typically ask me what formulas they need to have memorized. I would say memorize this formula and know that distance is equal to rate times time. That'll help you set up these problems. This gets used a lot in a bunch of different math classes. It's just useful for you guys to know. So, a Coast Guard patrol boat travels for 4 hours on a trip downstream or with the current, with a 6 mile per hour current. And on the way back, current still going 6 miles per hour. So let's set up two equations for this problem. we'll have one equation with the current and one equation without the current. So with the current, we know that the distance this boat travels is equal to its rate times its time. And the rate is going to be the tricky part here. Because as the boat is going down, the current is also going down. You can think of it kind of as my paper slides, my finger is also sliding. So the rate that they're actually traveling is equal to the rate of the boat plus 6 miles an hour for that current times the time of 4 hours. Now, without the current, that's probably not the best title for it. We could have a with and against might be a better way to think about it. Against the current, they're going to go the same distance. They effectively started in one location, rode the river to a second location, and then rode that river all the way back. So their distance is going to be the same. Their rate on the return trip, however, is going to be the rate that the boat would naturally go. But now it's fighting a 6 mile an hour current, and that took them 5 hours. So now we have two equations and two unknowns. We know that d is equal to r plus the quantity of r plus 6 times 4, and we know that d is also equal to the quantity of r minus 6 times 5. So if we know that r plus 6 times 4 is equal to d, and d is equal to r minus 6 times 5, well, that means that r plus 6 times 4 had better equal r minus 6 times 5. Now we're going to distribute 4 onto the 6 up and over addition to the r to give us a 4r plus 24, and then 5 up and over subtraction to get 5r minus 30. We want to get r by itself, so let's subtract 4r from both sides and add 30 to get 54 is equal to r. Now, r is the speed of the boat in still water. The boat will travel, or would, 54 miles per hour on still water. So our answer was not x is equal to 54, but it was this statement about the boat on still water. So that wraps up this section. That wraps up 3.4, solving applied problems. For motion problems, since it's in front of me, for motion problems, we're going to use that distance is equal to rate times time. And we're still looking for two equations we can set up with the information provided. For total value problems, and let me find one of those. There you go, that first example. For total value problems, we had an equation about how many, and then we had another equation about how much. How many and how much. For mixing problems, and I want to figure out where I put that one down. For mixing problems, we had an equation about volume, kind of like how many. And we had an equation about concentration, kind of like how much. Mixture problems and total value problems, for the most part, you're applying the same sort of idea to different situations. Your approach to them is going to be very similar. With concentration problems, remember that all of your percentages need to be converted into a decimal. But that's largely it for this section. Try and come up with two equations that give you information about two quantities, how they relate, and then try and set up these story problems. find it very easy to help draw. I find it very easy, or at least very helpful, I should say, to draw a picture for these problems. Pictures are a great way to get you going. I will never talk down on a picture. So try drawing a picture if you don't understand what's going on. And if you guys get stuck, shoot me an email. Even though we're not meeting face to face anymore, I'm still your teacher. I'm definitely still here to try and help you. I want to help you guys, so just let me know what I can do. Shoot me an email. Sorry, I kept on checking the camera, making sure I'm recording this time. But yeah, shoot me an email. Let me know how I can help you. If you're getting stuck on how to set up these problems, we can go over it. If any of the Chapter 1 or Chapter 2 material doesn't make any sense to you, sooner rather than later is a great time to ask those questions. We'll go over Chapter 1 and Chapter 2 material on the final, so it's not going to go away, and it might be harder to figure out the further away it is. So yeah, like I said, let me know how I can help you guys. I want to help you guys. I want to be there for you. We can't sit down and meet up for office hours anymore. But I'm more than happy to talk with you over email. We can have a phone call, whatever it takes, whatever you guys need, let me know, and I'll do my best to get that for you. We'll have a quiz. We'll have a quiz on Wednesday this week. Your quiz on Wednesday will be anything from 3.1 on to what I covered today, 3.4. Off the top of my head, coming into this quiz, know how to solve a story problem. Know definitely how to do elimination, elim, and substitution. Those are really graphing. Graphing is a very good method for solving systems of equations. They talk about trends. You lose a lot of precision when you do graphs. And also, it's really hard for me to get you to graph something for the quizzes now. Just the nature of Blackboard makes that kind of difficult. So definitely know how to solve using elimination. Definitely know how to solve using substitution. And know these setups. Distance is equal to rate times time. That's a formula you guys should have memorized. How far is equal to how fast times how long. And then these mixing problems, or total value problems. Yeah, like I said, let me know if you have any questions. Send me an email. From this section, from 3.4, go off and do 1 through 29, every other odd. This is going to be due on Thursday. And I don't have the date off the top of my head. I think Thursday is the 1st, April 1st, if I remember correctly. I could be mistaken. But this coming Thursday, turn in your 3.4, your 3.2, your 3.3, and your 3.4 homework will be due, and you'll take a quiz on 3.4. Yeah, I hope everyone stays healthy. Let me know if you have any questions, and I'm here to help you guys. Take it easy, everyone. Bye-bye.